Hello and welcome to 7.6, additional properties of triangles. We're going to skip 7.5 for now because I think this is going to be a little bit easier to do, and then 7.5 we'll wrap up the chapter with 7.5. Now the side splitter theorem is one of three theorems that we are going to learn. They're kind of based off of proportionality within triangles, and this first one will make life a little bit easier when it comes to triangles such as the one we see below. QRS, we have a triangle there, and then QXY, we have a bigger triangle, one triangle within the other. And the important thing here is that if we have a set of parallel lines within a triangle, then we could use this particular theorem. We call it a side splitter theorem, okay? Now, I'm gonna do this in pink. Do not copy this down, just follow along. If, for instance, we have RQ with a length of 4, Rx with a length of 2, QS with a length of 6, and then SY with a length of X. We don't know what it is. We know that these two triangles are in fact similar because of the parallel lines. We have corresponding parts, corresponding angles, and then ironically enough, Q would also be in both triangles. If we redrew them, we would have a small triangle QRS and then a big triangle QXY. Now, in this case, if we wanted to solve for X, we would create a proportion. 4 and 6 for the small triangle, 4 plus 2 makes 6, and then 6 plus x makes 6 plus x. We don't know what it is. And we would write a proportion accordingly. I've always said go left to right. So let's do that. 4 over 6 is equal to 6 over 6 plus x. And put that in parentheses as we should. And cross multiply, we get 36 is equal to 24 plus 4x. Bring the 24 over, and we get 12 is equal to 4x, or x is equal to 3. Now, if you notice something, Rx is exactly half of 4. 2 is exactly half of 4, and the same thing happens here. Sy, which we learned to be as x, is 3, which is exactly half of 6. And this is no coincidence. These side lengths have proportionality. Whenever we have this parallel line, or these parallel lines, we could actually set up a proportion using those particular sides. Now, be very, very mindful that you cannot do it with the set of parallel lines, okay? These two highlighted lines, I should probably use a different color. I'll make a note of it at the very end. But anyway, we could say, for instance, RQ, ooh, that's a highlighter. Let's do this. When we drew this, let's draw this for real this time. RQ, oops. RQS, and then the big triangle. XQY. We could say, since we've already done this, we could say that RQ corresponds to XQ. It creates a proportion with, what was it, SQ, because we went from small to big, over YQ. And this is only if parallel lines, or in this particular case, if RS is parallel to XY. This is the only case in which we could do this. Then these two sets are proportional. And let me highlight them. Let's do green with green. Ooh, make this a little bit bigger. All right. Green with green. And then let's do blue with blue. So we could set it up as so. Now, be very, very mindful. This cannot be done using the parallel sides, okay? I'm going to make a note here. This only works for the non-parallel sides. These are the non-parallel sides, okay? And a special note, this cannot be done with parallel sides. In that particular case, use the full similar triangles. As we have in the past, okay? So, if I did that problem again, okay, so I'm gonna put these values in. We already know what this answer is gonna be: 4, 2, and then 6 and x. We already know that x is gonna be 3, but we could actually do this proportion a lot faster. Instead of doing 6 plus x, we could actually set this up using this theorem. So I'm gonna use this theorem now. We're gonna do 4 over 2, which is RQ, is equal to 6 over x. Cross multiply, we get 12 is equal to 4x, divide by 4, and then x is then equal to 3. So we could see that it actually works. Okay, so that's what the side splitter theorem does. It helps us, it makes it in this type of problem a little bit easier to do because we don't have to do the full similar triangle. Okay, so that is your side splitter theorem. The next theorem is a corollary to the side splitter theorem. What that means is it's kind of just an extension. So corollary, oops, that's one R, corollary to the side splitter theorem. Now this is, like I said, it's just an extension. And what this means is what happens if we have not just 2 sets of parallel lines, but 3 sets of parallel lines. So I'm going to draw an even bigger triangle. What we could do now is we could set a parallel line here. That doesn't look very parallel. And one, let's say, a little bit here. So it kind of looks like a pyramid. So we have 2 sets of parallel lines now. Okay. Now, what I'm going to do this time, and it actually doesn't have to be a full triangle. You could even have 4 parallel lines, 5 parallel lines. It doesn't quite matter. The nice part, though, is we actually have proportionality between all of these small segments. Okay, so this is if let's call this line A. Let's call this A, B, and C for the lines. If A is parallel to B, which is parallel to C, then we could use this theorem. Okay, then we would say, for instance, let's give some letters here. Let's give this segment a name. Let's call this W. We could call this X. We could call this Y. And we could call this Z. What we could do now is, instead of using the full length of the side of this triangle, we could actually just use these parts individually. So what I like to the way I like to think about this is kind of looking at this parallel line as a fraction bar and putting an equal sign between this. So if you notice, W is actually over X, the length. So what we could do is we could say W over X, because this is that particular segment, over that segment, W over X is equal to, because it's that in between in the middle, Y over Z. And we have proportionality here, okay? And let's actually do this with some actual values. Let's pretend W, let's erase this. Well, let's not erase it, but let's actually put this in blue. Let's say W this time was a length of 9. Ooh, that's not right. Let's give this a length of 9. Blue, 9. And then for X, let's say this is a length of 6, okay? For Y, I'm going to give that a length of 12. And then we want to solve for Z. We don't know what it is. What we could do this time is we could set it according to this equation. 9 over 6, because W over X, is equal to 12 over Z. We could simplify this if we wanted to. This simplifies, or if we could just cross multiply if we wanted to. So simplify is always nice. make this 3 over 2. Cross multiply now. 2 times 12 is a lot easier. Oops. And as I say that, I do the math wrong. 3 times z is 3z. Divide by 3, and you get 8 is equal to z. Okay? So there we have it. That is the corollary to the side splitter theorem. Last theorem is something we are kind of familiar with. We know what this term means, an angle bisector. At least I hope we do. The angle bisector theorem. The angle bisector theorem. And in this particular theorem, we are going to take a triangle as so. And let's make it a little lopsided. Let's call this A, B, C, and then what we're going to do is we're going to split this angle on the top into 2 different angles. So I'm going to split this, try to split this as evenly as possible. That's going to be an angle bisector. I'm going to call that point at the very bottom of the base, D. And I'm going to split this into congruent parts. I'm going to put the tick markers here just so you know that they are in fact congruent to each other. What happens here is this. The angle bisector theorem says this. If AD bisects angle BAC, then, and this is a big then, these certain components will be congruent, okay? So I like to think about this as kind of like left triangle, right triangle, as I've said before. This is what we call the adjacent side because it's next to. This is the opposite side. If you want to just put letters here, you absolutely could. Let's do that. Let's use letters. I'm going to use W, X, Y, and Z again. So what we're going to do is we're going to take this, we're going to take these components, the adjacent side and the opposite side. We're going to put them, we're going to stack it in an equation. W over X is equal to, same thing here, adjacent side over the opposite side, Y over Z. Okay? And that is the angle bisector theorem. They are proportional. There's proportionality here. So I'm going to put in blue, I'm going to put in some values here and we could actually solve for it. I'm going to put a 5 here for W. I'm going to put a 3 here for X. For Y, I'm going to put a 15. And for Z, it's going to be an unknown. Using this theorem, we just place all the pieces according to their values. We do 5 over 3 is equal to 15 over Z, and multiply accordingly. 45 is equal to 5Z, divide by 5, and Z would then be equal to 9. And there you have it. There's the angle bisector theorem. So you could actually, you could do this. You could set this up a number of different ways, but this is the most basic form of it. Work with the components on the left triangle versus the components on the right. If you really wanted to do left to right, you could always do 5 over 15. So then I'll do this in pink. An alternate, as we've done in the past, we could always do 5 over 15 because they correspond with each other, is equal to 3 over X from left to right. So this is my left to right. Just make sure they're corresponding accordingly. Okay, so you could always do it like this as well. Simplify this, you get 1 over 3. 1 times X is X, 3 times 3 is 9, and you get the same answer. Actually, that should be a Z, but you get the idea. Okay, all right, that's all I have for you today. And if you have any questions, please let me know, and I'll see you in the next one. Bye.